Lenz's law. So, this basically states that a change in magnetic flux results in an EMF to oppose the new field created. And this is easily remembered by the fact that systems do not like change. So the current that results will go in a direction that minimizes the additional field that is taken away or added to the system. So here we have an example. So right now we're drawing a square current with a magnetic field that points upward inside of the area. The additional field is in purple. So there's a positive change in the magnetic field, which also results in a positive change in magnetic flux because the two are directly related. So we have two options, and we're going to ask y'all which one will happen. So our first scenario, so this is the system before, same thing on this choice. So in the first one, we have the option of the current going clockwise, and that's drawn in red. But in this one, maybe the current could go counterclockwise, and it's your job to figure out which one. Got the answer? So, due to the right-hand rule, if the current's going this direction, then it will induce a magnetic field that points downward, mitigating the positive additional field added in the problem. And on the bottom, if the current goes that way, then the additional induced magnetic field will add to the already positively occurring magnetic field, and this won't help the problem. So, number one would be correct. Because if you add a positive and you take some away, you're mitigating the additional. Because, remember that systems do not like change. So, the induced field will cancel out the added one. Now we have another problem. A 5 Tesla magnetic field directed out of the screen, so towards us, changes from 5 Teslas to 0 Teslas in 0.1 second. The EMF generated in a wire loop, 2 meters squared of area, and the average current if the resistance is 20 ohms. Figure it out. So step 1, we're going to write our equations. So let's see. So we have EMF equals the negative change in magnetic flux divided by the change in time. So that would equal negative change in magnetic field times the area divided by the change in time. The algebra way is a lot better. And so this results in, well, simple math. So just substitute. And we just did final minus initial for the magnetic field times area, which is 2, which is given in the problem, divided by 0.1 seconds. So after a little bit of math, you get 100 volts. And we figured out the units because EMF is basically like voltage in volts. And remember circuits? V equals IR still applies. So 100 equals I times R. And R is already given, so I must be 5 amps. And that's where we got from. So now, we answered Faraday's law. But Lenz's law deals with the direction. So our question to you really is, what direction is the induced current? And so you have two options, just like the previous problem. It can either go clockwise or counterclockwise. So here we have the circuit, and we have the outward pointing field in the middle. And that's basically what the problem gives you. That's the initial state. So the field B is already pointing out of the page, but it's decreasing. And remember, the circuit wants to keep its original state. So the current acts to restore the initial field, and that would be by increasing it. So we have to find the direction of the current that will add to the already existing magnetic field. So this is a quick right-hand rule problem. So just play with your right hand. And remember, it's because circuits want to resist the change. So if the magnetic field is decreasing, the circuit's going to want to increase it back to where it was before. So we figure out that the current is running counterclockwise. To regenerate the initial